Okay, so today we are going to take a look at this circuit that we have in front of us. At this point, we haven't really interacted too much with capacitors, but we're going to learn how to figure out how to find the voltage, currents, we're going to learn some important formulas for energy, and we're going to discuss one very important integral that we'll use quite often, so I recommend to become familiar with it. So the main goal of this video is to put an emphasis on the circuit analysis techniques and a little bit less on the integration. Like I said before, I will give you the general solution to the integral. Alrighty, so without further ado, let's go ahead. So, as I said in my previous videos, we definitely want to look at the circuit, see what we have in front of us, and kind of make sense of what we have. So, because we're being asked to find I1 and I2 and V of t, I have three elements in parallel. One of the things that I can tell right off the bat is that this is prime for a current division. Now, something to keep in mind, current division is based off of resistors, and resistors in parallel do not add like capacitors in parallel. So what do I mean by that? So let's write out the resistors formula for current division, and we can compare the two. So if I want to find some arbitrary current I of x is going to be equal to, let's call this Req divided by the R of x that I want times some coming I in. All right, now for the capacitor, and by the way, sorry, this is going to be for elements in parallel. And this also works for elements in parallel. So I'm going to say that I of x equals to my, let's use C. We're going to use C of x divided by CEQ times I incoming. So the main difference between the two is that these two have been reversed. Why is that? Well, it's because, like I said again, the resistors in parallel, two resistors in parallel, add differently than two capacitors in parallel. So these two capacitors in parallel are going to add like A1 and A2, whereas these two will add as 1 over A1 plus 1 over A2 whole inversed. All right? So going off of this, we're going to play some pretty nice tricks on this circuit. We're going to use the current division to find I1 and I2. Similarly, I can go ahead and just solve the CEQ. Actually, I encourage you to do that on your own after watching this video, and let me know if you come up with the same results. But the same circuit analysis applies, and it's even easier if you combine these capacitors. But for the sake of going through the derivations, let's go ahead and go to it. So let's go ahead and start with I1. I1 of t. I1 of t is going to be equal to my 2 microfarad capacitor divided by my 10 microfarad capacitor multiplied by the incoming current. Now the incoming current is going to be 240 times e to the minus 10t microamp. That is going to be my incoming current into this circuit. And like I've said before with current division, the current is coming into this and it's being split. This is the original current. So it's being split up. So we want to take a portion of the incoming. So the portion of the incoming current is going to be 240 e to the minus 10t microamp. Again, we can write I2 of t, like I2 of t equals to my 8 microfarad divided by my 10 microfarad times the 240 e to the minus 10t microamp. Alrighty, so we are going to use the voltage formula that your professors provided in the notes. So we're going to say that voltage equals to 1 over my first capacitance, and in this case I'm going to use the 2 microfarad, and we'll build from there. Also, it doesn't really make sense to do I2 of t because, or to find the voltage across I2 of t, because all these elements are in parallel, right? We know this from basic day one. All of these elements are sharing the same exact voltage. All right, they're connected by the two set of same nodes. So we're going to end up getting that we have 1 over c1 times the integral from 0 to t times my I1 of t dt plus my v of 0. So one of the things that this circuit is missing is the initial condition. So this v of 0 minus is actually going to be written in purple right here. V of 0 minus equals to negative 10 volts. Oh, let me write that a little bit neater. V of 0 minus equals to negative 10 volt. All right, now this is going to be super important. So we're going to go ahead and add this on right here. So these two are the same. All right, plugging everything in, we're going to end up getting 1 over 2 microfarad integral from 0 to t of, now after reducing the 2 microfarad by the 10 microfarad, I'm going to end up with 0.2 times my 240 e to the minus 10t microamp. And let me fix this piece, dt, plus my v naught. And my v naught was negative 10 volt. So I'm going to do a minus 10. Now, one of the things that I wanted to discuss was that if we have the integral of e to the minus at, this is actually going to be expressed as, the integral of this is going to be 1 over minus a, e to the minus at. All right, so using this property, we can go ahead and evaluate this integral. So for the sake of time, I'm going to go ahead and go to the solution. Solution is going to read that I have negative 2.4 e to the minus 10t minus 7.6 volts. All right, this is my v of t. So we've successfully found I1 of t, we found I2 of t, and now what we want to do is evaluate the energy. So let's call this part B. So when we're evaluating the energy, we're going to express it as W1 of 0. We're going to have a W2 of 0, and each one is going to be equal to 1/2 C1 times V of 0 squared, 1/2 C2 V of 0 squared. And plugging everything in, I'm going to have 1/2 times 2 microfarad times negative 10 squared, which is going to equal to 100 microjoules. Over on this side, I'm going to have 1/2 8 microfarad times negative 10 squared, which is going to equal to 400 microjoule. So in total, I'm going to have 500 microjoules of stored energy. Now, remember at the beginning of this video, I just expressed that the capacitor is going to be releasing stored energy. So this is what we're starting with, 500 millijoules, or microjoule, sorry. So what we're going to do now is compare it to its infinity value. So after a long time, the capacitor is discharged. How much energy is dissipated, right? So let's look at W1 of infinity. Now my infinity term is going to be this piece right here. And later on in another video, we can take a look as to why we're choosing this to be the infinity. It comes out of the step it and natural response section that we're going to be learning. So for now, let's take this 7.6 to be the infinity value. So we're going to have W1 of infinity is going to be equal to 1/2 C1 of V of infinity squared, which is going to be 1/2 times my 2 microfarad times my negative 7.6 volts squared, which equals to 57.76 microjoule. My W2, calculated in the same way, is going to be my 8 microfarad times my negative 7.6 squared, which is going to give me 231.04 microjoule. So in doing this, I'm going to go ahead and find the difference between the infinite energy stored and the original energy stored, or the energy stored after a long time minus the stored energy, in another way of saying it. So we're going to have W1 of infinity plus W2 of infinity minus W1 of 0 plus W2 of 0, which is going to end up giving me 288, which is this side right here, minus my 500, which is my initially stored, which is going to equal to my negative 211.2 microjoules. And just to recap everything that we've done, I've went ahead and looked at the circuit beforehand, and doing this guarantees that I'm going to save some time when doing this problem. I'm looking to find a circuit where I can do current division. I've done my current division correctly. Once I've done my current division, I've identified that I have elements in parallel, meaning that I only need to solve the voltage for one element, and I know the voltage of the entire circuit. Once I've been able to do that, I can then evaluate the energy using the initially stored voltage value and the voltage value that we've chosen to be W1 of infinity and W2 of infinity. All right, so that concludes this problem. There should be another video coming out shortly, so please hold on for that.